if you're looking for a way to calculate travel time for any place on Earth using OpenStreetMap data and then to create a very crisp travel time maps, this is the place for you. If you'd like to set up R like I have in VS Code, then you should definitely check out one of my previous tutorials where I explain step by step how you can do that. If you're new to R, I warmly recommend that you check out my video on setting up R in RStudio. And finally, if you are also working with other programming languages like myself, for example, Python, I think if you check out my tutorial on how to set up R in Positron, that's going to be also very valuable. All right, first things first, we're going to load the packages that we need. We're going to start off by using Pacman for that purpose. And Pacman is going to help us load, first of all, SF package for working with vector data, in this case, lines, OSM data for querying OpenStreetMap data. .jar will be using it for a routing graph of weights. Tidy geocoder we will fetch for geocoding, scales for label helpers, iGraph for graph components, map tiles for fetching the Basemap tiles, tidyverse and tidyterra for wrangling and plotting, and Viridis light for the Viridis palette, and ggspatial for the north arrow and also the scales. So these are the packages they'll be using in today's tutorial. There's quite a lot of them, but as you can see, most of them revolve around first of all working with graphs and then constructing this driving distance and then plotting that and creating the map. All right, after loading the packages, the next best thing we're going to do is define the parameters for the OpenStreetMap query. So we're going to be working in this tutorial with Barcelona in Spain, and we're going to be defining here the city of Barcelona as well as our starting point. For that, you can just go to the OpenStreetMap website and you can fetch for the names of your city or also places that exist in OpenStreetMaps. After that, we're going to be using 30 minutes for our maximum driving distance. And then finally here, we're going to also a bit expand our map by 5%. So that's why I'm adding here 0.05. In this step, we're going to be fetching the OpenStreetMap data in the SF format. And this is going to then help us actually perform the analysis. For that, we will be using .jar here. Now, what is very important here is that only have one .jar, so .r, and then the streetnet function from it. And then we're going to be passing here, of course, the city for which we want to get the data. We're going to be slightly expanding it, and we're just going to suppress any messages that will come by running this chunk. All right, so this is what you should be seeing here. We fetch the simple features object. It's a line string object, and it has here, as you can see, a bunch of fields. So 636 columns. We don't need all of them, but essentially, if you are exporting the OpenStreetMap data, you're going to get a lot of these columns here. We only need drivable roads. In other words, we don't need those that are like used for walking or cycling. So what I'm doing here is I'm actually defining, based on the values from OpenStreetMap data, only those roads that can be accessed by cars. And then over here, I'm basically saying highway is something that's in the OpenStreetMap dictionary encompasses all of these types. So what I'm saying here, if these types are present in the highway column in our data, then just keep those roads. We are not going to take any other street types that are not drivable. And then over here, what actually you need to do is then you need to basically define this highway column and say that you're just going to be filtering only those. So filtering only those that belong here. So this is a very important step so that we also minimize the amount of data that we need. All right, in this step, what we're going to do is we're going to be converting our street SF object into a weighted edge table for routing using the motorcar profile, so speed or penalties by highway type, and we're going to be keeping the highway column. The reason why we're doing this is going to create numeric edge costs, so distance d and the time w, which actually are essential for creating this shortest path for isochron calculations later on. That's why here we're using weighstreet function for that, and we are defining here profile as a motor car, and we are also keeping the column which is highway. Then in the next step, what we're doing is choosing the weight column. So time W in seconds, if available. Otherwise, we're going to be using the distance D meters. So this actually makes the rest of the code robust if the time column is absent. All subsequent filtering uses a single chosen metric. And then in this last step, what we are doing is we are dropping edges which are missing, zero, or negative weights, because this prevents that divide by zero and infinite distances later are not going to be used at all in our code. So this is a very important step. And as you can see, I'm calling this graph all and making sure that they are finite. So using this is finite. And then also as an additional argument here, I'm saying that, so using this graph all, I'm saying that the weighted column needs to be greater than zero. Again, that means that it needs to exist, so it should not be missing, and it needs and should not be a negative value. Now, if you check actually how this new object graph all looks like, you will see that there are here a bunch of features. What we are interested in are these from ID to ID. So basically, these are the points that we're going to be using to actually connect to each other. And of course, the coordinates from lon and from lat. So from longitude and from latitude, and to longitude and to latitude. Again, this is going to help us find those spots in the coordinate system. And as you can see here, there's also a time weighted, and there's also the distance weighted, because we're interested in the time to get to a certain point within half an hour. Then we will be definitely using here time weighted. All right, so in this part, what we're going to be doing is keeping the largest undirected component. And to do that, we have to do several steps. The first one is create this edges basic as a data frame, because it will extract the simple edge list IDs only. We are doing this one to actually build an undirected graph purely to find connected components within that graph. So speaking of the components here, what we are doing is we are simply, defining, okay, so these are my from and to points here. So in the second step, we're going to be defining the components themselves. The first one is going to be this GUG. And for this one, we're going to be using iGraph, a graph from data frame. And basically what this one is going to do is going to build an undirected graph for us. Then the second one is going to find the components of that graph. And for that, we'll be using components from the iGraph package, and then just passing this undirected graph that we previously created. So UG is basically undirected graph. The third one is going to be finding the largest component, or a giant component in this one. And then the fourth one is going to be about, listing all the vertex IDs of this giant component. The reason we are doing this is because railroad networks can be fragmented. So what we want to make sure is that by keeping this giant component, we ensure that the origins can reach most places. So avoiding some isolated places or some broken, lines. And then in this last part, what we're going to be doing is we're going to be filtering the weighted edges to only those that are entirely within this giant component. And why we are doing this? We are doing this because this actually enables or guarantees connectivity for distance calculations from the origin. We came now to the part where we're going to be making the graph effectively undirected. In the previous step, we defined those components that we need. We also single out the giant component. We made sure that everything is connected to the giant component. But now what we're doing is making a function which is called make undirected as a function of the graph that we will be passing here. So what this function does in a nutshell is it duplicates every directed edge in reverse. And then it swaps the coordinates if they are present. And as you can see here, what we actually do is, well, in the first steps, what we do is simply we define the graph that is going to be this reverse. And then, but you can already see in the next step that when we define this from ID, the from ID is basically takes the value of to ID from the graph. That's why it means we are doing it in reverse. So we're going to be doing that for all of the X and Y options. So we have X from, Y from, X2, and Y2. So we essentially also need to swap those. As you can see here, this is what we're doing. So for example, this one. So rev and then X from is going to be get the value from this graph with X2. And then all of those four options are going to be like that. So this is the first step that we're going to be doing in this function. And then once we do this deduplication of every direct edge in reverse, then the next step will be to actually merge and deduplicate rows. we're going to be defining this keep. So this is what we want to actually keep here. And the keep is going to be the intersection between the names of our graph and the names of this reverse object that we created. Finally, what we're keeping here is, as we say, deduplicating, meaning keeping only those rows that are unique and then putting all the together from the graph and from this one. Now, what is the reason we are doing this? This is because some of the OpenStreetMap edges are one way. And if for a symmetric, for example, how far I can drive in X minutes, we often want a bidirectional approximation, so from to a point. So this function basically ensures reachable sets don't get artificially blocked by directionality. So that's why we, in the first place, we define this, unidirectional graph. And that is a very, very important part here. Now, in this final part, so outside of this one, we are finally calling this function. We are applying to our graph, and we are creating this graph UD, which means undirected graph. And then in the last part of this is what we're doing is we're extracting the vertex table once we have that. So with all the IDs in coordinates. So once we create this undirected graph, we're now extracting using this dodge R vertices. And the reason we are doing this is that because we need a clean vertex index to snap the origin to and to compute the distances to every vertex. Okay, so we have the undirected graph, but we now really need to make sure that we anchor our points in something that really exists on the map. So it should not end up somewhere else, it should really end up on the street. That's why here we're calling to rescue Tidy Geocoder, which is going to help us geocode the origin, so for every dot, and then snap to the existing component. So what this actually does that we are doing here is we're passing this origin based on these addresses, and then we're using the string via the OpenStreetMap, and then we're going to be returning one latitude and one longitude values for each of those. Of course, at the end here, what I'm doing is I'm just suppressing here the message, but that's basically what it does. So the point of this one is we want to convert human readable address into coordinates to anchor our analysis, in short. Then we're going to actually convert this into an SF object. So we're going to be making the origin a point SF object in this WGS84 format. So we need to define longitude and latitude and also 4326. We're doing this because spatial operations, nearest feature, require SF geometry. Then we're going to turn the vertex table also into the points. And they're going to also be SF objects. So we're going to essentially be doing the same thing here. And this is going to allow spatial nearest neighbor search between the origin and the network vertices. And then in the final part here, what we're doing is we are finding the nearest network vertex to the origin and assigning it its ID. So this is what we're doing. And why are we doing this? We're doing this because a routing must start from a vertex that lies exactly on the graph. As you probably noticed, there's like a lot of stuff going on here, but don't worry, this is simply because of the type of analysis we're doing. So we're working with travel time, but we need to really get things in order. And one of the things we need to do here is travel times in minutes on this undirected motorcar graph. So the first thing we're doing here, we're going to be copying this time weights, W, typically seconds, into these D columns. And why we're doing this is because by default, Dodge R uses distance. So we don't need distance, we actually need time. So this makes actually a distance matrix return time instead of meters. Then in the second part, we are computing the shortest travel costs from the origin vertex to all the vertices using the D column. And this is the core Eisenhower ingredient, so time to every vertex. In the third part, we are doing is converting seconds to minutes. That's why we're dividing by 60, because by default, Dodge R returns seconds. So by doing this, we're going to get minutes. And then in this part, what we're doing is here with this V times is that we are building a simple, just a lookup table. So the vertex ID tell us what is the minutes from origin, because this will then help us because we want to attach these times to the edges for the mapping. So for every of those, we're going to have that. So that's basically it. And then in the rest of this code, what we do is we simply here define what is our ID. So this is the vertex ID. We define the time minutes, which we already defined, and string size factor equal also false. This is the last data wrangling part before we actually create a map, but it's a very important one because we are going to be building the edge geometries and join times here. The first step we're going to do with this edges try object that I'm doing here is we're going to try to convert our existing graph into an SF object. I'm using dodge-r to SF and just passing our undirectional graph here. Now, if this doesn't help, I'm also creating this second one, which is edges SF. And over here, I'm then trying to do it, to build them manually. So if the first one does not work. Why are we actually doing all this? We're doing all this for a very simple reason. It's because we need geometries down the line to draw roads in ggplot2. Okay, so if that conversion in the previous step did not work, then in this step what we're going to do is create a fallback, which is going to help us rebuild geometry if needed. So if the previous step did not really work. So what we're going to be doing here is we're going to create this if statement, and then what we're going to be saying here, if if we actually did not create anything, so if the number of rows of this edges SF equals 0, then we need to redo that manually. This is the only reason why we are actually going through this, if the previous step did not succeed. So what we're doing here is, first of all, we're going to defining vertices from and to, and we are creating them as a data frame. They are going to inherit, of course, the vertices IDs. Of course, they're going to have also this longitude from and latitude from. The same thing, literally the same thing, we're going to be creating this vertices to, but instead of having the from ID and instead of having the x from and y from, we're just going to have, to ID and x2 and y2. So this is when it comes to vertices, and then after that, after this is defined, then we're going to go ahead and add more into this. So the reason why we're actually doing this is this guarantees that we still get drawable geometries even if those helper utilities fail. So in the next step, we're creating also this gmin object, which is basically going to be a data frame from this from ID and to IDs from our undirected graph. And this is exactly what we're doing here. After that, so after we now defined the v from, v2, and this gmin, and all of them are data frame objects, then in this fourth step here, we're going to be actually just merging everything together. And we're going to be merging under this gmin. So we're going to be passing here the gmin, and we're going to be passing here this v from, and then we're going to be merging them using this from ID. So this is the column that is common to both, and then we're going to be keeping everything from this gmin. Then after we merge that, we're going to be doing the same with gmin and this vertices 2 data. And the only thing we will change here, of course, is the column name. It's going to be a different font, so it's going to be the 2 ID. And again, we're going to be keeping everything that exists already from the X, so the first object, which is gmin in this. Okay, so now that we merged together these three objects, so we have our undirected graph, we have the vertices from and to, we want to make sure that the values, all those 4 values related to x from, y from, so the coordinates, that they are finite values. And this is exactly what we're doing here. So we're passing here that the condition for this filter is that the values for the x from, for the y from, and y2 and y from, that they're all finite. So that basically when we start connecting these dots, that they actually have the ending and that they have a start. So they're not kind of a loose. Now, this is going to be our filter. And then we're going to be using this filter after that to actually drop those that are not finite values. So everything from the gmin that does not meet this criterion is going to be now dropped using it like this. So everything needs to be finite, in other words. Now, once this is done, we're going to be creating this line list now that we have all these components. And because this is a list, we need to use this lapply to apply a function. And this function, what it's going to do is it's going to coerce everything into a line string. Since we're going to be working with lines, and the line itself is going to be, of course, composed of 4 parts, which is the x from, y from, x2, and y2. So this is essentially what we're doing here, defining simply, this is coerced into line string, but the line string is a matrix of these four points in space. Now, as you can see, there's a lot of now brackets, so be always sure that you close the brackets in a proper place, because if you don't, the function is not going to work. It's going to throw an error. That is a very important thing here. But essentially what we are doing here, we are guaranteeing that we'll still get actually drawable geometries with the beginning and with the end, by filtering out those that are non-finite values. And of course, this is going to have 2 columns, and I'm also putting by row equals true. And once this is done, we finally want to, of course, go ahead and use this to pass to the edges SF. So we are defining here what is the from ID, to ID, and because it's an SF object, also needs to have geometries. So it's going to be basically, it needs to have the geometries from the line list, and it needs to have also the WGS84 coordinates reference system, which we have been using since the beginning. So once we actually have now this edges SF object with those merged vertices, we're going to do a bit of a, first of all, data wrangling or cleanup. We want to make sure that, because we want to join times from the 2 endpoint vertices, we want to also make sure that they are, first of all, the same column type. So we're going to go ahead here and just coerce them into a character like we did also before. So we're going to do that from this from ID and also the to ID. And once we do that, then we're also going to make sure that there is also the geometry column here. And we want to put this, so to create a table, a data frame, so we're also going to then drop this geometry. So that's exactly what we're doing. So this is simply a cleanup for the next step, which is basically creating a lookup table. And to create a lookup table, first of all, why do we create this lookup table? Well, lookup table is actually a very good way, a simple way to color an edge by how soon you can reach some points on it. And the lookup table in our case, what we're doing here is we are first of all looking up the travel minutes for each of these edges. So that's why I'm actually putting here, we're setting the names, unique names for the travel minutes and then the ID. And then what we're then doing based on that, we're going to be, well, first of all, we need to do this unname. So we need to unname each of these. So we're going to be doing this for travel to and the travel from, and also the travel edge. So there are going to be 3 objects here, but essentially it is the same. It is the same exercise. So we're going to be just unnaming T from and T to. And then once that is done, for the edge itself, we're going to be actually calculating the minimum. So minimum from, and time to, and we are going to be removing the missing values. So why are we using the minimums here? We're using the minimums to actually avoid gaps due to the endpoint asymmetry that can happen, as we know. All right. And then once this is done, what we need to do is define, of course, the geometry. And then once we define the geometry column here, we can go ahead and put back this into an SF object. So that's why we're using st as SF from the SF package. And we are passing here our edges data frame. And we are then also defining the geometry column. And at the end also we're defining here the coordinates reference system, which is 4326. Okay, and in this very last data wrangling step, we're going to be keeping only edges with valid times inside this cutoff window. So we're going to be filtering, and we are doing this filtering because this is going to create the reach within X minutes subset for the final map. So we're going to be getting rid of everything that is infinite, so that cannot be created here. And this is exactly those 2 conditions that we're putting here. So it needs to be equals to or lower than the maximum minutes, which is 30. Everything above that we don't care about on the map. And of course, the values need to be finite values. We're getting ready to create our map, and the first step will be to fetch the Basemap tile so that our map looks nicer. So we're going to be using map tiles to download the raster Basemap tiles covering the edges, and it's going to be in the pseudo Mercator, so EPSG 3857. So we are doing this because this is going to provide us actually context with roads and labels on the map, and it's just going to look much better. So what we're actually doing here is we're taking this zoom, which is going to be a pretty high zoom, so we want to zoom in really into the streets. So let's actually quickly just inspect how this tiles look like, if this zoom level is appropriate for us, and let's just use from Terra this plot RGB and then just pass our objects. Okay, so this is how it looks like. I'm pretty happy with the level of zoom here. We can see the main streets, and we can even see the labels of some of them. A very important step before we proceed is to convert our edges object into the same coordinates reference system, which is this pseudo Mercator, as our base map. Because if you don't do that, you are going to end up with your lines being on a totally different part of the map, with only the base map being shown. Okay, we're moving on to the phase where we're going to be defining the discrete color scale for our project. But before we do that, we're going to be just creating here a local alias for clarity. So we're going to be just keeping the plotting code tidy by just, making sure that we have here this clone. We're still defining the color palettes, and in this one we're going to be first of all building the pretty breaks in minutes. So 5-minute steps, 0 to 5, 5 to 10, etc. To do that, we first of all need to create 5-minute bins. So that's why I'm putting here from 0 to the maximum cutoff, in our case 30 minutes, and it's going to be by 5 minutes. So it's going to be 0 to 5, 5 to 10, 10 to 15. What is actually important here is it should not go over 30, and that's why here I'm saying here should not be greater than, should be lower than maximum minutes. Then we are defining then from to those breaks, and then we also want to assign then this to our edges plot. So we want for every edge to have also these values so that they belong to these different categories. The reason why we're doing this is you could also have a continuous one, but I feel that this is kind of a more intuitive legend, which is going to really help you gauge, oh, okay, so this is in this range. Rather than, thinking, oh, maybe this is like 5, maybe this is 10, this is 15 minutes. I think like really bins help you, define or see what belongs to what category. And then over here, what we're going to do with these labels, we're going to, as I say, prettify, or basically just make them human readable. We're going to first of all define them as separate ones, so as levels, and pass to this LVL object. And then we're going to be creating these pretty labels, so that we have 0 to 5, 5 to 10, etc. So for all of them. And that's, in the next step, this is going to show on the map itself. And then in the last step here, we're going to also be setting the names for these pretty labels using, of course, these levels that we created. The reason why we're doing that is really ensures the legend shows, 0-5, 5-10, etc. all the way to 30. All right, it's plotting time. So first of all, let's define one of the parameters here that you can then, change in your code. And this is going to be that the road width is going to be 1.25 millimeters. You can change, of course, that one, but I'm going to start with this one. Then we're going to be calling to rescue tidy Terra and adding that base map that we loaded before, as you remember. Because tidy Terra allows us, without even transforming this into a data frame, we can directly pass it. Then we're going to add our next layer, which is going to be lines. So this is our main layer. So over here, we want the colors to be based on the travel categories, which we defined in the previous step, and this is what we are doing. And we want to have a constant line width, and that's why I'm passing here this one. If you want this also to correspond to the time categories, you can also pass that. There's some also kind of beautifying things here, so we want the line end and the line join to be around, and we don't want to give it complete non-transparency. So we want to put it, for example, alpha 0.9. Instead of being completely visible, there's going to be a bit of transparency here. Then we're going to be using Viridis color palette, And over here, we're just kind of customizing some things. For example, we're adding here a legend name, legend title, to be more precise. We're going to go for the magma palette. It's a bit kind of a more pronounced, but you can check out there's some other Viridis palettes. What is very important for Viridis is it is colorblind friendly palette. So you can use different ones. And also here we're defining our breaks and we are defining our labels. Then we're going to jump to the next part, which is going to be a bit defining the theme. We're going to be using, of course, the pseudo-Mercator coordinate reference system. So that's something we put here to this chord SF. And then we're also, for the theme, we're going to start off with the void theme. So without any, axes and labels on the side. All right, moving now to the rest of this theme, we're going to customize this even more. We're going to play a lot with the legend here. So the first thing we're going to define is that the legend position is going to be on the right-hand side. And then we're going to also readjust the size of our legend keys. I'm going to be using here the size of 8 millimeters for the key height of our legend. And because it's the same size for the width of the keys, I'm just going to go and copy and paste here and change this. Then for the legend text, because it's a text, we need to tell that to ggplot2. I'm using this element text attribute. And then defining here size. So the size is going to be a bit smaller but still visible. For the title, I'm going to choose a bit larger title size, a font size compared to the text of the legend, and I'm going to make it bold. And after that, we can also define the size of our fonts of our plot title and also our plot subtitle. So I'm also doing that, so just like a bit of a customization here with these different font sizes. Of course, feel free really to customize this and see what works for you. Of course, also readjusting a bit the horizontal justification of our subtitle and also our title. What is a map without a scale bar and the north arrow? We're going to be adding that right away using the ggspatial library. So first of all, going to be adding the scale bar. And for this one, we're going to be putting this one into the bottom left part of the map. So that's why I'm defining here the location equals BL. And also I'm defining here a bit of a, I would say, smaller width of it, so that does not occupy much of the space, and also a bit smaller size of the fonts. After that, we are going to also define the north arrow. Now for the north arrow, in terms of the location, it is going to go into the top left corner. So it's going to be on the same side of the screen, but it's going to be on the top, while the annotation scale or bar scale is going to be on the bottom. And then we are also going to here choose a specific style. You can check out ggspatial and especially this function for the north arrow, and maybe choose some other styling if you're interested in that. Then we're going to wrap up this with the labels. So we're going to define here the title. Now for the title, what I actually am doing here is you can, based on the input at the beginning, you can put the name of your city without changing anything here. So you can change it at the beginning, just put the name of your city, and this is going to be then reflected in the title of the ggplot2. I found this kind of more reproducible than what I used to do. So essentially what I'm doing here is I'm using this maximum minutes, putting in here. So saying in the title, okay, so this is the drive time for this number of minutes and for this city. Then for the subtitle, you can then also use, what is the origin here. And if you remember, we also defined the origin at the beginning for Barcelona specifically. And then finally, in this labels, you can also define your caption. In the caption, you can put the source of your data, which is exactly what we're going to do. That for the Basemap, we're using the Carto DB. And then for the data itself, we're using the OpenStreetMap contributors. You can also add, for example, if you want the author or anything else in the caption. So let's export our map. For that, let's first of all define what is going to be the name of our file. So over here, you can again reuse what you had at the beginning. So the name of your city or your town of interest, and then just pass it here. So literally this is gonna help you. You don't need to spend time manually typing here the name of your file name. You already defined it at the beginning of your code. And this is what we're just passing here. It doesn't even need to be this. You can also choose your own file name, but I just found this kind of to be more reproducible. Then after this file name, you can also define, of course, you need to define what is the plot you're going to save, but you can define the width and the height. And I'm just going to go here for the standard 7 by 7 inches, and I'm going to also take a bit higher dots per inches, so I'm going to take 600 here. What is very important here at the end is choose the color of your background. So if you don't choose, it's going to be transparent, and it's not going to look nice. So what I do here is I always go for the white background.